we can actually analyze such a system by using its body plot. Okay? So here, you might remember that sometimes if g of s, h of s is, for example, 1 over s, s plus 1 and s plus 2, you might remember the following figure here. It is Nyquist plot is looking like this. At low frequencies, it is starting from minus 90 degrees, and as the frequency increases, the magnitude and phase changes, and we get to a minus 270 degrees. Such a plot is called a polar plot, and it is part of the Nyquist plot, which corresponds to the positive part of the imaginary axis. Okay, part of the imaginary axis corresponding to positive frequencies. Remember, I can actually complete this Nyquist polar plot into a full Nyquist plot by adding also the parts at infinity. Okay, but here we might actually stop at the polar plot, and we have here the point minus 1. In order to be able to discuss stability, we are looking at the encirclements of the point minus 1. In general, this polar plot can be actually passed into a body plot. Okay? So at each point, for example, at each point I look at the magnitude here. This is the magnitude GH. The length of each point on this contour here, each point on this curve corresponds to a specific frequency. And the distance of that specific point from the origin gives us the magnitude of the frequency response, and the phase of that point would give us the phase of the open loop frequency response. Okay? In general, we show these in separate plots, which would give us a body plot. So this is the same thing. We can plot the frequency response in a polar plot like this by putting the magnitude and the phase in this manner. It is called a polar plot, and it's part of the Nyquist plot that we can draw. But we can draw the same thing by taking the magnitude and the logarithm of the magnitude, by plotting the magnitude in dB scale like this, and by drawing the phase in a separate plot like this. Remember, we have defined some specific frequencies for that are important for us. For example, the frequency at which this polar plot intersects the line, the negative real axis, is really important. So when the angle of g of j omega, h of j omega, is equal to minus 180, this is called what? This is called some crossover frequency, but which crossover frequency? This is where phase is crossing minus 180 degrees. That means that this is phase crossover frequency. Okay? So here, the gain at that point of the system determines the gain margin of the system. Okay? The gain margin for the system is going to be 1 over the magnitude of the system at this phase crossover frequency. Okay? So this is the linear scale. Or if I look at the same thing in dB scale, it's going to be minus 20 log g of j omega p, h of j omega p. Okay? Well, this is called the gain margin, and this is in dB scale, and if this thing is positive, the closed loop system is stable. The more positive this quantity is, the more stable we call the closed loop system. Okay? And we need to have this thing a positive quantity, meaning that this magnitude should be smaller than 1 for stability, because if it is not smaller than 1, then we see that there is no encirclement, and that is going to give us a closed loop stable system. And the second thing is that is important for us is called the phase margin. Phase margin is determined by the frequency at which this polar plot intersects the unit circle. Okay? So here we have g of j omega and h of j omega. When it is equal to 1 or when it is 0 dB, then we can determine the frequency at which this actually happens. This is called the gain crossover frequency, and the phase at that point determines the so-called phase margin of the system. Okay, so I can draw a line here, and I can look at it. It is phase. The phase margin of the system is defined as this angle, okay, from the negative real axis. Again, the larger the phase margin, the more stable we call a closed loop system as. And here, the phase margin is given as the angle at the gain crossover frequency, j omega g, h of j omega g, and I add a 180 degrees here to that angle. Okay, so here, if this angle is minus 100, for example, then I would have 80 degrees phase margin. Okay, so then phase margin should be positive again for a stable closed loop system. We can do the same things that we do with the polar plot by using a Bode plot. If I would like to determine, for example, the gain margin of the system, I look at where the phase crosses minus 180 degrees. We see that in this case it is crossing at 2 radians per second. So here, phase crossover frequency is 2 radians per second, and when I look at the magnitude there, it is 20 dB. The negative of that is minus 20 dB, and that means that the gain margin of such a system is minus 20 dB, meaning that the closed loop system with this open loop Bode plot then is going to be unstable. And when I look at the gain crossover frequency, I look at where gain crosses 0 dB line. And we see that this is 2, 3, 4, 5. So it is somewhere between 4 and 5 radians per second. And when I look at the phase margin here, I look at the phase there, which is going to be approximately minus 225, meaning that the system has minus 45 degree phase margin, meaning that the closed loop system is indeed unstable. Okay? So here, why do we use such a Bode plot instead of this type of plot?
Easier to interpret.
It is easy to interpret. That is one of the reasons. But what is going to happen is that into this closed loop system, I'm going to place a controller. Okay? In addition to the open loop system here, I'm going to put a controller into the system. In that case, I will combine the controller transfer function with the actual system transfer function, g of s. Okay? And I will here h of s here. Okay? And I will put here also an additional gain. In general, this controller will not include any gain, but the gain is going to be separated from it. So in general, the controller design is going to use this type of figure. And in this case, in addition to GH, we are going to get K and GC of S in the open loop system. Okay? What is going to happen to the system Bode plot, open loop Bode plot, when I include a K here? The magnitude is going to be shifted up or down depending on whether K is smaller than 1 or larger than 1. Okay? And what is going to happen to GC of S? This is going to have its own Bode plot. Okay? And when this has its own Bode plot, when I look at the magnitudes of these two things, the overall Bode plot is going to be the summation of the Bode plots of the open loop system plus the magnitude of the Bode plot of GC of S. Okay? So when I have the GC of S Bode plot, sometimes it's going to be looking like this. For example, in the first controller that we will think about, it's going to be looking like this. And this is going to be the Bode plot of the controller that we are going to be using. And here, for me to be able to draw the overall Bode plot of the open loop system, I am going to add the magnitude plot of the controller Bode plot to the magnitude plot of the actual plant Bode plot. I will add the phase of the controller Bode plot with the phase of the actual plant Bode plot. So everything is going to be added. Controller design is going to turn into what to add into those border plots to make the phase margin larger, for example, into a value. For example, here we have seen that I have the phase margin minus 45 degrees. Suppose that I don't change the magnitude, then if I can add some phase to this system, if I can add some phase here, just like this, some positive phase, then I will be able to increase the phase margin of the system. I will be able to make it positive. If I add a large positive phase to the system around those frequencies, then I will be able to make the phase margin of the system much larger than its original value. I will be able to actually stabilize the system in that case. Okay? So here, another way to increase the phase margin is to decrease the gain, for example. Okay? If I decrease the gain, what is going to happen to the gain crossover frequency? If I decrease the gain of the system, it's going to move to the left or to the right? When I decrease gain, this zero crossing is going to shift to the left. Okay? But we see that the system has larger phase at those frequencies. Okay? So the phase margin is going to automatically increase actually if I reduce the gain somehow. So another controller that we are going to use is going to have the following type of border plot. Magnitude is going to be negative and phase is going to be negative. One controller is going to be called phase lead compensator. It is going to increase the phase margin by boosting the phase of the original system. It has positive phase. The other controller is going to be called phase lag compensator, and it is going to achieve a larger phase margin by reducing the gain of the system at high frequencies. Okay? So here these are going to be our controller, and we are trying to go there now. Okay? We haven't seen anything related to those controllers yet, but we are trying to reach those topics. So when we look at a border plot, what is important for us are these three things in different regions. Stability and performance of the system is usually determined by the medium frequency range. So where the gain crossover frequency and phase crossover frequency, usually the transient performance is determined by those parts of the middle part of the border plot. The low frequency region determines the steady state performance of a closed loop system. It is reasonable because as at the steady state, this S variable and the frequency should go to 0. So low frequencies actually determine the steady state behavior of the system, and high frequency region determines the performance of the system under noise. If the system has large gains at high frequencies, then this means that the system is going to amplify noises in your system, which is usually not a very good thing, because noise has high frequency. In general, we want the gain of the system to be reduced at high frequencies as much as possible. So here we can actually look at the type of the system by seeing a magnitude border plot. In general, this is also apparent when we look at the phase curve. But when we look at the magnitude curves of a border plot, we can actually see what the type of the system. If GH has the following form, it is in border form in this case. I have T1S, 1 plus T2S, etc. And I have 1 plus tau 1S, 1 plus tau 2S. This is the GH in border form. And when at low frequencies, I know that at low frequencies, these S-related terms will be negligible, and everything here is going to turn into just 1. And at low frequencies, this transfer function is going to be approximately k over S to the n. Okay? And when I look at the magnitude of this thing, the magnitude is going to be k over omega to the power n, and the phase is going to be, when I substitute S equals to j omega here, what is going to be the phase of such a transfer function? K over j omega to the power n. What is the phase of this thing? Minus 90 times n. Okay? So by looking at the phase or by looking at the magnitude, we will be able to determine the type of a closed loop system by looking at those Bode plots. Okay? For example, if the slope of the curve Bode plot at low frequencies, if it is 0, what can I say about the type of the system? So here k to the omega n. If I look at the dB magnitude, it is going to be minus 20. I would have log k, and I have plus 20 log k minus n 20 log omega. So when I look at this magnitude with respect to log omega, it's going to be aligned with n times minus 20 slope. Okay? So here when I increase omega 10 times, the slope, the magnitude is going to be decreased by n times 20. Okay? So this actually means that the slope of the curve is going to give us the type of the closed loop system. Okay? If the slope is 0, what is the type? 0. If slope is minus 20 dB per decade, what is the type? In that case, we have type 1 system. And in this case, we have the slope is, in a decade, the decrease is approximately minus 40 dB at low frequencies, meaning that this is a type 2 system Bode plot. Yes, so the slope of the magnitude plot will give you the type of the system that is required for steady state analysis. And similarly, when you look at the phase, if it starts from minus 90 degrees, if the phase starts from minus 90 degrees at low frequencies, what is the type of the closed loop system? 1. So if the phase starts minus 270 degrees, what is the type of the system? It's a type 3 system in that case. So here we can determine actually for the steady state analysis, we can actually determine what type of static error constants we have by looking at the Bode plots. Okay? So here we know that for steady state error to unit step input, we are required to calculate, for example, what Kp is. Kp is static position error constant. And it is determined as the limit of the open loop transfer function as s goes to 0. Okay? For different types, so I know that a steady state to unit step is 1 over 1 plus Kp, and Kp is that limit for different systems. I have here 3 different systems with their magnitude plots. Okay? I can determine these Kp's for each of these systems by using the Bode plot. So here you have to think that currently we don't have any transfer function for the open loop system, but we have its Bode plot. And if I have its Bode plot, I can calculate this Kp without actually knowing the transfer function itself. Okay? So this is a type 0 system. What is Kp for this system? It is going to be this limit as s goes to 0 gh. This is the Bode plot of magnitude plot of gh. What is the magnitude of gh as s goes to 0 for that system?
20.
It is 20 dB. 20 dB in linear scale is 10. So here Kp is 10 for system 1. Okay? So for system 2, I need to look at what Kp is. The second system is a type 1 system. Okay? So its transfer function contains just 1 over s here. N is 1 for that system. What is Kp for the second system? Here there is a common mistake. If you just read this value, it is 60. In dB scale, in linear scale, this is 1000, 10 to the 3. Okay? So if you write there 10 to the 3, it's going to be wrong. Because here, this limit is taken when s goes to 0, when the frequency goes to 0. Various frequencies 0 on this plot. It's at minus infinity, at a block. Okay? So what is the value there? It is infinite. So Kp is infinite. This is a type 1 system. It has to give zero steady state error to unit step input. Okay? That is why this has infinite Kp. What about this one? It has again infinite Kp for the third system. So now let us try to look at Kv. The steady state error to unit ramp input is given as 1 over Kv. And Kv here is the limit as s goes to 0, s times gh in this case. Okay? So now I have to calculate this limit for each of these systems. The first one is a type 0 system. What is Kv for that? Kv for the first system, what is it? 0. It is going to be 0 because gh goes to a finite non-zero value here, and you are multiplying it with s, meaning that when I let s go to 0, this thing is going to give me just 0. So Kv is 0 for the first system. The second system is a type 1 system because the decrease rate is 6 dB per octave or minus 20 dB per decade. Okay? And now we can actually try to calculate what Kv is for that system. So in general, it requires you to concentrate on low frequencies in a body plot. So I see that the second system has the following form. GH it's a type 1 system. So we have an S here, we have some K's here, and I will have some terms that are not going to be important for us. 1 plus tau 2s, etc. And 1 plus t1s, 1 plus t2s, etc. This transfer function is in border form. At low frequencies, if I go below any of the corner frequencies here, if I go into this region, in that case, which terms I can approximate as 1? All of these terms are 1 at low frequencies, okay? So these are 1, etc. So this transfer function is approximately k over s at low frequencies, okay? And when I take the limit s times this thing, when I take that limit, what should I get? Just k, right? So here, Kv is equal to k. So the thing that I have to do is to read from that body plot. I need to read the internal gain k of the system from that body plot. For that, I'm going to concentrate on the low frequencies. This is k over s. So I'm going to concentrate at a low frequency here, where there is some known intersection with one of the lines here. Okay. So here, so on this grid, I see that at this low frequency, for example, what is this frequency? 0. This is 0.2, 2 times 10 to the minus 1. So the magnitude here is k over omega. When I substitute j omega here, and when I take the magnitude, I would get k over omega. At omega is equal to 0.2 is what? It is 40 dB. 40 dB in linear scale is 100, okay? So that means that k over 0.2 is 100, meaning that k, which is equal to kV at the same time, is 20 here, okay? So concentrating at low frequencies in a body plot like this will enable you to be able to read this, internal gain of the system actually. Okay? You will get rid of all of these terms which are coming from non-zero poles or zeros, okay? And they will be negligible at low frequencies. Okay? So here their effect will not be shown, and you will be able to calculate this type of gains, kV, by concentrating on that plot at low frequencies. And what is kV for this system? It is infinity, because this is a type 2 system. There is an s square here. When I multiply it with s, and when I let s go to 0, the result will be infinite. Okay? So in general, what we are going to concentrate as the performance measure in our design is going to be the phase margin. In general, this phase margin has a relationship with the damping ratio of the system that we can think of. In general, in control systems, we don't want the damping ratio to be very small. Okay, for example, a damping ratio which is around 0.5 or 0.6, or the least one might be 0.4, for example, we can use in our systems. For a second order system, there is this type of relationship between the phase margin of the system and the damping ratio of a system. Okay? So for example, if the phase margin is 50 degrees, then the approximate damping ratio of a system is around 0.5. It is barely acceptable, actually. Okay, so we would actually, as our performance measures in controller design with body plots, we are going to use the phase margin, and you can think that this is related to the damping ratio of a system, and you don't want it really small, okay, for good transient performance. And when you try to look at the high frequency region of body plots, usually we interpret our system as a filter. Okay? So in general, when you look at the body plot of the closed loop system, in general we will only look at the body plot of the open loop system in this course, and we will forget about the body plot of the closed loop system. But here is an example of the closed loop system magnitude plot after some controller design. Okay, and we see that it is looking like a low pass filter. It passes everything of interest until a frequency, and it doesn't pass high frequencies. We don't want it to pass high frequencies because we don't want our system to be affected by some noise terms. Okay? So in general, after our design, our system closed loop magnitude response would be looking like this. And this cutoff frequency here of this low pass filter is generally approximately equal to the gain crossover frequency of the open loop system. Okay, so in the body plot of the open loop system, if you locate the gain crossover frequency, then you would approximately find the cutoff frequency of the closed loop system. So here, if this is my input to a low pass filter, this is unit step input. Okay, if I give this input to a low pass filter, what kind of response would you expect? There is a sharp change here. Okay, and this sharp change represents some high frequencies. Okay, if I pass this signal from a low pass filter, then you would see that it is going to turn into something like this. This sharp edge is going to disappear, and I will get something like this. Okay, so this is a low pass effect. So we can think about our closed loop systems as low pass filters. Okay, taking unit step input, and then it's going to be converting this into this form. So if I increase the cutoff frequency of the low pass filter, what type of response would you expect? If I increase the cutoff frequency, then we start to get an almost all-pass filter. Then what is going to change in my response if I increase the cutoff frequency? It is going to be closer to unit step or further away from the unit step? Closer to the unit step. If I increase the cutoff frequency, the system is actually going to be faster. So we see that as we increase or decrease the gain crossover frequency of a system, we are going to be changing the transient performance of the closed loop system. If we increase the gain crossover frequency, which increases the cutoff frequency of that filter, our system is going to be faster actually. And if I decrease the cutoff frequency, then my response is going to be actually slower. Okay? In that case. So in some way, there is a relationship between this gain crossover frequency and, for example, the rise time of the closed loop system. Okay? So this is related to the bandwidth of your system actually, which is related to the cutoff frequency. So in general, that is for making our system, control systems fast, we want to increase the cutoff frequency of your system. But in general, because there is noise in the actual system, real system, increasing the cutoff frequency makes your control system susceptible to the noise inputs. Okay? So here, if increasing the cutoff frequency is good, then I can have as large cutoff frequency as possible. Okay? But there is a trade-off there. We really do not want the cutoff frequency to be very large, because in such a case, your control system would be amplifying the noise inputs that it is given with, and that is going to be bad for performance as well. So there is a trade-off here in frequency domain. Any questions? So let us write phase lead compensator. So now I will first try to actually motivate a phase lead compensator. If you have a compensator in the following form, 1 plus, let us say, TS. What type of controller is this? What type of controller is this? It is only proportional, so this is a P controller then. Yes? This is a PD controller. Okay? So this is our PD controller, and when I look at the frequency response of a PD controller, I'm going to get the following: J omega T here. So this is a first order type of term. And where is the corner frequency of this thing? Where is the corner frequency? Corner frequency is at 1 over T here. So when I look at it, its body plot, I'm going to see the following. So I have the magnitude, and this is my, let us say, GC of S, okay, evaluated at S equals to J omega. So this is my corner frequency 1 over T, and this is my 0.1 over T, and this is 10 over T. Okay? Until the corner frequency, this term is going to be negligible. Okay? Until the corner frequency, for small frequencies, then corner frequency, this term is negligible, so we have 0 dB. Okay? So this is the magnitude of GC of J omega at all frequencies. And here at the corner frequency, what is going to happen? So for large frequencies than 1 over T, we see that this term is going to be negligible, and this thing is going to turn into J omega T. What type of asymptotic body plot it's going to bring to us? I need to decrease with minus 20 dB per decade. Here, the magnitude should decrease. Should decrease or increase? It has to increase with which slope? 20 dB per decade. Okay. So here we see that the slope is going to increase here, and actually it's going to continue increasing forever. Okay, with 20 dB per decade slope. Okay. So here, do you think this frequency response for our controller is fine? When we don't have any noise in our system, this is quite fine. If we are working here, if the input frequencies are somewhere here, then we are going to get a nice derivative effect here. But there is usually some noise here at very high frequencies. Okay? So if this is the input that I'm going to give to the system, usually there is this type of noise which is going to come on top of that input. Okay? So noise is somewhere here in frequency, and the signals of interest are somewhere here. Okay? So do you think this type of transfer function for a controller is fine for us then? It's not fine. Why is that? Because the noise here is going to be amplified with a very, very large gain. Okay? I won't like this. Another disadvantage of a PD controller is that this derivative operator, unfortunately, it is not implementable using passive components. Using only resistor, capacitor, and inductor, you can never implement a passive derivative operator from voltage to voltage. Okay? From voltage to current, you can maybe implement with a capacitor or inductor, but from voltage to voltage, you can never implement an integrator with passive elements only. So that means that in order to be able to put this controller into your system, you have to actually spend some energy, or you have to spend some power. Okay? So here it is because of this derivative term. In order to be able to avoid these drawbacks, we really do not like this type of increase of the frequency response to infinity as frequency goes to infinity. What type of change would you suggest in this case? What can I do to limit that increase to infinity?
Another corner frequency decrease.
Yes, I can put here another corner frequency. Where? Here?
At a high level.
At high frequencies, if I give myself another corner frequency, and in this case it is going to be a corner frequency for a zero, or it's going to be a corner frequency for a pole. It has to be for a pole, right? So here that is what it is done actually indeed. So GC of S is going to be 1 plus Ts and 1 plus alpha Ts. Okay? So here, this is called a phase lead compensator. And here, the corner frequency is going to be the following. GC of J omega is 1 plus J omega T, 1 plus J alpha omega T. So where are the corner frequencies? Corner frequency of the zero is at 1 over T. Corner frequency of the pole is 1 over alpha T. Okay? So these are the corner frequencies. I want the corner frequency of the pole to be larger than the corner frequency of the zero. 1 over alpha T should be larger than 1 over T. Then what is the criterion on alpha that should be satisfied for satisfying this inequality? Then alpha has to be between 0 and 1 here. Okay? This is called a phase lead compensator, and T is positive here. Okay? Is always positive. So now let us try to look at the frequency response of this thing now. So I have omega here, and I have the magnitude of GC of J omega here, in dB scale, of course. So now I will mark the corner frequencies. The corner frequencies are going to be 1 over T and 1 over alpha T. Okay? And I will put here, just for the sake of simplicity, 10 over alpha T, and I will put here 0.1 over T. Okay? Now let us try to draw the magnitude response of this compensator. By the way, compensator is the same thing as controller. Okay? It just terminology changes in control literature. That is why we use it. I can actually call it a lead controller. It really doesn't matter. So here, I am going to draw again the magnitude. At low frequencies, if omega is going to 0, what is the magnitude of this thing? It is 1 in linear scale. What is it in dB scale? It is 0. So until we hit the lowest corner frequency, the magnitude is 1, so we have 0 dB magnitude. At this frequency, we still haven't reached the corner frequency of the pole. That means that the pole is still remaining at, the pole related term is still remaining at 1, okay, at this frequency. But for the 0 related term, this j omega t part becomes active now. Okay, that means that we are going to increase here the magnitude with 20 dB per decade slope, okay? Until we reach the corner frequency of the pole now, okay? We are going to reach this second corner frequency. At that part, how am I going to continue with my asymptotic plot? It is going to be a straight line, just horizontal like this, okay? So now, for large frequencies, what is the magnitude here? Let omega go to infinity in that transfer function. What is the magnitude? Tell me the number in linear scale. It is 1 over alpha. So here, this limiting value of the magnitude is 20 log 1 over alpha. Alpha is between 0 and 1, meaning that 1 over alpha is larger than 1. Okay, so that this is a positive number when I take the logarithm. Okay. So now let us try to look at the phase of this thing. So I have 1 over t, 1 over alpha t, 10 over alpha t, and 0.1 over t. If I was doing the same thing for the PD controller, what would be the phase? So here, until this point, for the PD controller, I would have just the following. So at the corner frequency, we need to have 45 degree phase. Okay? This thing has 45 degree phase at the corner frequency. And it is going to have almost zero phase here, and then it's going to increase, and it's going to pass 45 there, and then at 10 over t, we're going to have the phase approximately equal to the phase of this thing. What is the phase of this thing? 90 degrees. So we're going to reach and settle there, 90 degrees. This is the PD controller phase. Okay? What about the phase lead compensator? So in that case, the phase is going to be 0 for low frequencies. But when we go over the frequency 0.1 t, this pole term would still bring us 0 phase because we are still not close to the corner frequency of the pole term. So this 0 is going to start increasing the phase. Okay? So we're going to come here and the phase is going to increase. If this pole was not here, if this corner frequency was not here, then we would go and pass through and go to the 90 degrees there. But now, because of this 1 over alpha t corner frequency, what is going to happen? Phase is going to start decreasing, right? So from a point. So we're going to have a phase given like this. All right. So this is a phase lead compensator. So and we see here that there is going to be a frequency at which we are going to have a maximum phase lead here. Okay. So here, this frequency I'm going to call as omega m, and the maximum phase lead that we can get here is going to be called as phi max. Okay, that is phi max. Yes.
You said that we can implement an integrator with passive elements.
An integrator or derivative. You cannot implement it from voltage to voltage or from current to current using passive elements only.
So phase lead compensator is the same, right?
For the phase lead compensator, you can actually implement it with passive elements. Okay? That is one of the advantages. Using only resistors, capacitors, and inductors, you can implement this thing. So without actually spending any power, you can implement your controller. If you want to use PI or PD controllers, you have to spend some power. So only using an op-amp, you can come up with a derivative circuit or integral circuit, and your op-amp is going to spend some power. Okay, but these compensators can be implemented with passive elements only, meaning that you don't have to spend energy for your control. So here, how are we going to use this thing? In general, we are going to have a magnitude plot and we're going to have a phase plot. This is for the plant itself. Okay? So here I'm going to have minus 180 degrees, okay? So here I have minus 180 degrees. And let us say that phase is given something like this, okay? So this is the magnitude of the plant, g of j omega, and this is the phase of the plant, okay? This is argument of g of j omega. When I use this compensator, what is going to happen? That magnitude is going to be added here, and that phase is going to be added here, okay? So currently, this is my gain crossover frequency, and when I go and when I look at the difference between this phase and minus 180 degrees, this is going to be my tiny phase margin. I won't like this phase margin in my closed loop system. That is why I am going to use that compensator to increase my phase margin to a required position. Okay? For example, this phase margin is going to be approximately, let me say, 5 degrees. But in my requirements, I'm going to, for example, need 60 degrees phase margin. This means that I need to increase this phase by 55 to a value somewhere here. I'm going to benefit from this compensator by placing this peak phase lead around the gain crossover frequency of the system. So I'm going to try to add that thing into this one to get a large phase margin for the closed loop system. But unfortunately, there is a side effect here. And the side effect is going to be the following. When I add this phase here, somewhere around here, peak phase, unfortunately, this positive magnitude is also going to be added into the system. Okay? This means that as I try to increase the phase margin of the system, the gain is going to increase as well, and the gain crossover frequency of the system is going to shift to the right. Okay? And if the phase of the system is going to be reduced slightly there, so I'm going to lose some of the phase that I added there. Okay? So here, in the phase lead compensator, we are going to benefit from this phase increase, but magnitude is going to be a side effect for us that we are going to try to overcome. And for example, if I want to add here 55 degree phase, then I'm going to choose these parameters alpha t such that this peak here is going to be approximately 60 degree. Okay? So I'm going to add a 60 degree phase to the system, and this magnitude is also going to be added. We are going to try to overcome the side effect of that magnitude addition. That's all for today. Thank you very much.
Hocam kazık zaten her zaman 3 point yapıldığı için yakınlıkta 5 point'te kabul edilir. Yani bazı değerli
Daha ek 3 çizerseniz ne hala. Ama yani ben şu anda hiç şeye dikkat etmiyorum açıkçası.
hep 3 point
Alfa yani şuraya koysaydık, 1 bölü alfa t'ye koysaydık, 1 bölü t'yi böyle koysaydık.